I'm so excited about this session. It's about Arduino Robotics. So the title is Exploring Pedagogical Approaches in Arduino Robotics Through Hands-on Experience by Nurul Hazlina Noordin. She's an associate professor in the Faculty of Electrical and Electronic Engineers Technology at UMPSA. Uh, Nurul, the floor is yours.
Hi, Stomatis. Okay. Thank you very much. Thank you very much. Let me share my screen. Okay. So hello again and hi everyone. Firstly, I would like to thank the organizing committee of the IEEE 2024 STEM Summit for selecting this work as one of the presentation for this year. I feel really honored and glad to listen to the interesting talk yesterday and today by fellow speakers this year. So my name is Nurul Hazlina Noordin from the Faculty of Electrical Electronics Engineering, UMPSA STEM Lab, University Malaysia Pahang Al Sultan Abdullah, Malaysia. So today I'll be sharing our experiences in exploring pedagogical approaches in Arduino Robotics through hands-on experience, focusing on programming, digital making skills, and embedded system. I'll start with a little introduction about UMPSA STEM Lab, and then I'll go through a bit on the pedagogical approaches that we had implemented earlier. And also I'll touch a bit on black box versus white box approaches in Arduino Robotics, in robotics in general. And then we will go through a bit on the hands-on activities that we had done in the lab, and also future direction, and a conclusion towards the end. So basically, UMP STEM Lab is a lab that has been set up in the Faculty of Electrical Electronics Engineering, University Malaysia Pahang Al Sultan Abdullah. It serves as a hub to enhance STEM education, mainly focusing on digital making skill sets. So we do activities like outreach initiative, extra co-curricular learning opportunities, as well as a mentorship program. So participants are empowered with the knowledge and also hands-on experiences. So normally in these kind of activities, we will always bring in the lecturers from the faculty, as well as the undergraduate students as mentor in the engagement with the school children. So the digital making skill sets that we covered, mainly covering these four main domains, from three-dimensional design to programming to manufacturing, as well as physical computing. So it begins back in 2016. And as we evolved, we started in the early days, we started off with the activities that teach Arduino programming, and mainly dealing with on how to control output using sensors, just to spark interest among school children, and to get them to work on with electronics component as well as programming. But as we evolve, slowly we include more advanced module, and in addition to the Arduino, we started to introduce Python programming, where participants explore deeper in the computational thinking. And then as we move on towards 2020, 2021, we started to bring in Arduino Robotics module, which allow students to build and program robot for delivering tasks such as line following, line tracer, and also sensor-based interaction such as obstacle avoidance robot. So throughout the years, we built from the module, and up until today, up until 2023, up till last year, we have recorded around 13,000 participants throughout our outreach program all over Malaysia. So what is Arduino Robotics? So Arduino Robotics is propelled by the Arduino, which is an open source platform, and it is an easy use hardware and also software. So it is designed for everyone, whether at a beginner level or at for expert. to build digital device and interactive objects that can sense and control both physical and also digital component. So the core of the system is the microcontroller board, as you can see here, which can be programmed to control inputs such as from sensors and also process the input and give outputs to blink LEDs or motors and also to put display. So what makes Arduino particularly effective for teaching is because of its simplicity and flexibility. Now, by flexibility, I mean the accessibility. The hardware and the software are affordable. That is the main criteria because it is affordable and it is open source and it is easy to learn, making it as a low barrier entry point for students at all levels. So with accessibility as the advantage, we can do a lot of hands-on learning. And via the hands-on learning, we can encourage students to engage with electronics in a hands-on way. So students can build circuits, writing simple programs, and also students can immediately see the results of their work, making learning tangible. Okay. So while Arduino is a powerful tool, how we teach it is just as crucial as the tool itself. So the pedagogical approaches are the framework that guide teaching methods and learning outcome in robotics. They shape how students engage with the material, and why pedagogical approach are the key to develop STEM core core STEM skills is because by doing these hands-on activities, we can build a strong foundation skills. Secondly, is that we can make engagement and maintain a good retention rate. So hands-on project-based learning keeps students engaged by making learning interactive and relevant. So students are not passive listeners. While learning, they do things and also they see the simulation and they experience the robot movement and do the troubleshooting live. And this indirectly motivates and also cultivate critical thinking among the students. And in robotics especially, students must often troubleshoot issues and find creative solution, whether it's debugging the code or figuring out how to make the sensor work, even to understand how the sensor is not working. So these challenges indirectly build their critical thinking skills and teach them on how to approach problem methodically. Okay. When teaching Arduino robotics, the pedagogical approaches play a critical role, as mentioned earlier. There are three core methods guide the learning process. So the first one that can be adopted is the most widely used is project-based learning, PBL, and then embedding the corpus learning theory and also implementing tiered scaffolding. So together, these approaches ensure students not only grasp the technical skill required for robotics, but also develop critical thinking, problem solving, and also hands-on in understanding real-world problem. Okay, so for project-based learning, what we did was that, project-based learning is an educational method that emphasizes on active learning by placing student as the center of the problem-solving process. So rather than simply following instructions and memorizing facts, students engage in meaningful and hands-on projects that mirror real-world challenge. So in Arduino Robotics, problem-based learning is implemented through several ways, such as learning by building and completing project. So students learn robotics by programming, as I mentioned just now, whereby they can program, take the input from the sensor, and also control the motor of the robot so that the robot can fulfill tasks. So an example of the real world implementation task is such as to code the robot so that it can follow certain pattern or it can follow lines. And another important aspect is that the end-to-end learning, whereby students follow the entire process of a project from conceptualization through completion. So this includes design the robot functionality, building the circuits, programming its behavior, and testing it in a real-time environment. Okay, let's touch a bit on the COPS learning theory, whereby this theory emphasizes on learning through experience. So in general, there are four stage or four processes that involve in COPS learning theory. So the first one comes from the concrete experience, whereby engaging directly with robotic tasks, such as assembling a robot, programming it to perform specific function. And later we move on into to reflect the activities that we had done earlier. So students are encouraged to reflect their experience in two ways. Either they explain on how they do the coding, or they visit their friends who are also doing the project and try to troubleshoot together with the friend to troubleshoot if there are any errors. So this encourage these reflections, and learning via reflection is also one of the way that is being emphasized under this concept. And the third component is the abstract conceptualization, whereby based on the reflections from participants, they can draw conclusion and generalize the concept that they had learned. So for instance, they may come across to understand how specific sensor work, such as the IR sensor or the ultrasonic sensor, and why certain programming language is necessary for robotics movement. And the final component, or the fourth component from this scope learning theory, is active experimentation, whereby students apply their newly acquired knowledge, understanding these new challenges or iterations of their project. For example, after they had fixed their initial problem with robot navigation, for example, they may experiment with adding new functionalities, add on. For example, if let's say previously they were using only like for IR sensors, but with ultrasonic sensor, perhaps they can add on more functionalities to the robots. Okay. The third framework that is being implemented is tiered scaffolding, whereby it is a method of gradually introducing complexity in the learning task, which allows students to build skills incrementally. So in Arduino Robotics, this approach is key to helping students master the fundamentals before moving on to sophisticated projects. So at the initial stage, whereby we normally term this as workout programming, students are provided with step-by-step guidance. For example, they may start with how to lead up the LED on the robot, with detailed instructions on how to connect components with basic codes. This help them to not only build their confidence, but also be familiar with the platform, with the layout of the Arduino IDE, and with the concept of uploading and also implementing into the microcontroller before getting the robots to work. Secondly, we move into debugging specific malfunction. So as the student progress in doing their robotics project, they are introduced to troubleshooting and debugging. So for instance, if while doing the activities, the robot motor isn't working or isn't running as expected, they learn on how to troubleshoot or find the potential code or the wiring issues that may cause this problem to happen. So this helps them to develop problem-solving skills, and try to be resourceful and try to address the issue. And as the student progress, we move on into the semi-completed programming task, whereby at this stage, students are provided with examples code or partial codes, and they try to complete the code and build a deeper understanding to the concept. And last but not least, in the final stage, where we remove the scaffolding, And the students are being tasked with building and programming new project from scratch. So at this stage, they are expected to apply all the experience that they had gone through earlier and try to build the complete project, whether it's designing a robot to follow line or navigate a maze. This foster innovation, critical thinking, as well as autonomous learning. So at this stage, normally when we implement in the lab, we can see that the students go beyond the module giving them the access to the internet, and with the open source norm of the Arduino platform, there are a lot of resources that they can bring in into the project, modify them to make it work as what they intend this to be. Okay, next I would like to touch a bit on the black box and also the white box in robotics as general, especially to the novice learner. So when teaching robots with Arduino, it is important to consider on how learning experience is structured. So there are two contrasting pedagogical approaches, whether to use the robot as a whole unit, or we normally term this as black box, or white box approach, in which we go in depth into the component inside the black box. So each of these white and black box offer distinct advantages, challenges, and also learning outcome for students. So the black box approach focus on using robot as learning aid to acquire skills such as computational thinking without diving deep into the internal working of the component. So students engage with a pre-built model or module of robots, and try to solve challenges such as line following robot, obstacle avoidance, and also maze solving robot. In this approach, students preliminary develop logical thinking and also acquire programming skill or programming techniques. In contrast, the white box approach treats a robot as transparent element. So where students build and understand each component from scratch. This involves deeper exploration on the internal working of the robot, such as to design the internal circuits to connect the sensors, and integrating microcontrollers, or even having additional microcontrollers if we want to add more sensors into the robots project. Now, this approach, no doubt, it will allow students to gain in-depth knowledge of hardware, giving them insight into how each component contributes to the robot's overall function. Now, one of the drawbacks of having this black box approach is that it is limited by the availability functions of the robotics module or package or any platform that we use in the activities. It also relies heavily on the robot existing technology, which can restrict creativity and also deep understanding. On the other hand, the white box approach, um, while it offers deeper understanding, it requires significantly more time, as students have to build each and every part of the robot themselves. This would include constructing the controller board, such as the one shown here, up until setting up voltage divider circuits to drive motors, and also integrating sensors, solder the IR sensors, and other working sensors as well. So normally when we do outreach program, one of the issues that we face is that we only run these as extra co-curricular activities, and time constraint make the white box approach more challenging to implement. For our undergraduate students, of course, the white box is always the methods that we use. But for a program with school children, this can be very challenging. Additionally, for young novice learners, like as school children, and also whether it's primary or secondary school students, the white box approach can lead into cognitive overload. There are too many things to learn at one time. So since everything is new, comes from programming or hardware, it can challenge their attention span and engagement. So to address this, we try to find moderate solution. So these are the advantage and also the comparison between the two approaches that I mentioned just now. And to address this, we try to find the middle line whereby we look into a modular approach in order to balance the strength of both black and white box. So what is the modular approach? Okay. So before I go to the modular approach, so this is an example of the of a two-wheel based robots that we had used before, and which represent the black box approach, whereby students focus on this pre-built robot, and the primary objective when doing this kind of engagement is to focus on the programming, the software part, as well as minimal hardware and computational thinking through challenges such as obstacle avoidance or line following robot. Um, this is an example of the white box approach, whereby students design from scratch, they assemble all the components, they attach, solder, build a working structure, and also code, and also integrate sensors, and make the hardware programming. Um, and as we move towards the years, we find out that the best way is to find a modular approach whereby we can balance these both black and white box paradigm. So the robot, the one that I've shown, the four robot on the right hand side here, offers the benefit of hands-on learning, whereby a custom PCB board is created, and which integrate core components such as the motor drivers, voltage regulators, as well as the microcontrollers connections. So this modular design allows students to plug and plug and connect different sensors. For example, in this robot, we have attached the ultrasonic sensor. Beneath the robot, there are 5 sets of IR sensor, which enable them to code this robot to become line following and obstacle avoidance robot. As they become familiar with this platform, they can slowly change or add on other sensors with minimal changes to the PCB board. As we spare a couple of auxiliary pins so that they can custom and they can add on components later on. So this is the example of the activities that we normally do in the engagement, which normally takes around 14 to 15 weeks of 2 hours engagement per session. So we started off with the first part, getting them to be familiar with the tiered scaffolding approach, whereby they learn on to be familiar with writing, uploading, debugging the code, while maintaining the robot as a black unit, as a black box unit. And then as they had gained confidence, we started to introduce sensors, whereby they start to plug in sensors and make the robot to interface with the sensor, LED, motors, and also applying fundamental principles of circuitry. Some of the sensors that are on the board, they are not purposely made not to complete. So the students have to start to learn on how to make voltage divider and started to engage with the existing module. And lastly, when they are pretty much comfortable with this setup, we start to give them assignments such as to make an autonomous line following robot, and to start to apply a couple of obstacles in between, and how to make that robot to move autonomously. Okay. Okay, so as I mentioned just now, the key challenges when doing Arduino robotics, what we want them to learn in depth, is the time constraint. And secondly is the cognitive overload. So because there are a couple of things that need to be implemented before they can be comfortable to program the robot as a whole or as one unit. Okay, One of the, as I shared just now, the solutions or what we had seen work so far is by implementing a structured progression, hand holding them in the beginning, but slowly start to release the scaffold, and towards the end, that would give them some confidence to be independent in programming the robot. And also, it is important to have active support. So these kind of activities, I normally engage quite a number of undergraduate mentors, so that they can be active and be present with the school children. Okay, one of the way forward that we look in implementing integration to the robot, this include having data literacy whereby when the sensors on robot collect data, we like for this year's engagement, we start to introduce database and also start to introduce the student with integrating that database and try to display that via dashboard. Secondly is that I think it is important to participate in such program that we are having now, because it will give opportunity for us to learn from the best practices from others as well. And okay. So as a conclusion, what I've shared just now is some experience that we had done, especially in implementing hands-on learning experience with Arduino Robotics, and also the tiered scaffolding approach, and trying to find the balance, the modular approach, and the impact that we have on students, and also future direction. And last but not least, I mean, the progress that we had done in UMPSA STEM Lab so far is made possible by the strong support that we have had from various parties. I would like to take this opportunity to extend to thank you, UMPSA as general, and also the Faculty of Electrical Electronics Engineering, all the industry partners, both locally and internationally, as well as the government and non-government organization, who played a very crucial role in this journey. Um, so um, I would also like to thank again IEEE for this opportunity to present in IEEE Summit, and also to the Ministry of Education Malaysia, and also state and district education officers for participating in the program that we had done before. And also a very special thank to all the undergraduate student mentors, school teachers, and also students who had participated in this program. We look forward to continuing this collaboration and working together to inspire and nurture future innovators in STEM. Well, thank you very much.
All right, thank you so much, Nurul. It was a very interesting presentation. And we've got a lot of questions, but we're out of time. We'll try to address one or two. So, did you find your methods work better for a particular target group, say different ages, study levels of the students, etc.? Um, for example, was it easier for primary or secondary school students to be more engaged?
Okay, all right, okay. So, okay. All right. I find out that the platform that I had shown earlier, so in the beginning of the engagement, we started to introduce the white box approach. We find out that that is not suitable for novice, whether it's primary or secondary school students. It depends on their experience of prior experience handling with hardware. So I think the best approach for primary or secondary school children, if they are novice, is the modular approach, whereby they start to learn and use the robot as a black box unit. But as they started to be familiar with at least the Arduino platform, Arduino IDE, they can slowly convert into the modular approach. And once they are familiar with the hardware and also with the software, then we should go to the white box approach, whereby they start to build from scratch.
Okay.
Okay.
Any other question?
Okay.
How do you recommend balancing hands-on work with theoretical learning in robotics?
Okay. So I think this one it is reflected via the tiered scaffolding approach. Um, it should go hand in hand. What I mean here is that when we do engagement, of course, they need to have certain foundation or certain theory in hand, but don't overload with too many things, too many information. For example, when we start out with the module, perhaps let's say, for example, we wanted to introduce analog input, maybe we can start with IR sensor. With IR sensor, we can start to introduce the analog concept and also the analog input and try to relate that with the robotics application. So then when they are familiar with one sensor as a unit and that one sensor be implemented on the robot as a functional unit, then we start to move to another sensor. So what I can respond to the question about the theory and also the practical. I think it should go hand in hand, and we should plan that whatever theory that we cover, it should be followed by a hands-on or the practical work.
Okay, thank you so much. We are out of time. We have to have a break and then move to our keynote session. Thank you so much. It was a
Thank
pleasure
you.
to have you. We'll try to download the questions and send them to you so that you can answer and we can send them to the attendees. Thank you so much.